Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. This is the last lecture for the electron beam lithography. So this is the part 4. And then today we're going to talk about the way of we are increasing the throughput using the same electron beam lithography technology. So one of the way people can increase is throughput using electron beam lithography is using the electron beam like an optical lithography. It just use a much bigger diameter of the electron beam. So use as a projection. So we call that as an electron projection lithography, like an EPL. And then another one is we just make this big electron beam as a much finer, small portion of the beams, which is a multiple beam. So using this way, we can also increase the throughput. We reviewed from the previous 3 lectures. We don't have any problems for the resolution using the E-beam lithography. And then alignment accuracy, we don't have any problems. But we always have problems in throughput, the number of the wafers we can handle per hour. For example, in the most of those kind of advanced optical lithography tool used for the commercial chip production, it can handle more than 100 wafers per hour. But this E-beam lithography cannot meet that kind of a throughput. So, as I talked in the early of the lectures, EPL is the one of the option. There is 2 types called as CALPL, which is scattering with angular limitation projection electron beam lithography developed by Lucent Technology. Actually, I'm not gonna go very details about these techniques. So the more detailed techniques you can find from this website. And then another technique is developed by IBM, and then that is projection reduction exposure with variable axis immersion lenses. So that is the second method using this electron projection lithography. So, as I just briefly mentioned, this electron beam projection lithography use very big diameter of the electron beam. And then this is the combination of the electron lithography and optical lithography. So it has some kind of a physical mask are present. So this kind of electron beams just pass through this mask and then just transfer its patterns on substrate, resist-coated substrate. So the way of people are making this mask is a little bit different from optical lithography. So for the optical lithography, when people just have patterns, that is transparent areas and then non-transparent area, and then those kind of 2 different area, just making different kind of a pattern transfer, and then based on the resist type, those kind of patterns are just transferred differently. But electron beam is not photon, so we do not use this kind of a transparency for making mask. So for making, giving some kind of a contrast between those 2 area, exposed area, and then non-exposed area, people use different kind of material. So people use a light material, and then also people use a heavy material. So light material make the electron beam scattering much less. So when people use very thin light materials, those kind of electron beams can pass through directionally without making severe scattering. But if this material is kind of a heavy material, when the light electron beam just try to pass through, it just scatters and then just changes the direction. So in this kind of electron projection lithography, we put apertures under the mask. So this kind of scattered electron beams cannot pass through the apertures and then cannot reach to the substrate. So that's the way people's creating this kind of a contrast. So there are two versions of the masks. So this method, it uses this kind of a membrane. So it has on the light material, has on this kind of a membrane, and then we form this kind of a heavy materials on top. And then for these techniques, it's just using this kind of a stencil form of the mask, so which does not have a membrane. And then the thickness of the membrane is only 100 to 200 nanometer thick. And then this observer layer with the heavy material is on about 50 to 100 nanometer in thickness. So if we are making this structure as a 4-inch mask size, if then this membrane, considering this kind of a very thin thickness of the membrane, this mask itself is kind of very fragile with this kind of very big area. So that's the kind of one of the big problems out of this kind of electron projection lithography. And this view graphs just wanted to show you what's the differences of those kind of electron scattering based on the two different kind of materials. So when we use the light material, silicon is lighter than gallium arsenide. In this case of that, this kind of a lateral scattering is kind of much smaller than that of the gallium arsenide. So in a little bit more exaggerated drawing, those kind of light materials again pass those kind of light materials much more directionally, so it can just reaches to the substrate. And then this kind of heavy materials, it just scatter with a much larger angles, so it cannot, it just collected at the aperture underneath. So but the problem is this kind of electron beam is kind of very high energetic beam. So that is why it can damaged by those kind of electron beam. So sometimes those kind of electron beam just making some kind of charge build up. So those kind of charge build up distort those kind of electron beam, because this kind of a charge build up, if this area is kind of built by those kind of local charges, if then when the electron beam coming down, these kind of beams can be distorted. So that can be a problem. And this kind of high energetic beam also making some kind of just considering those kind of a very thin thickness of the membrane, it can just physically just to deform those kind of the membrane, so it can just make the patterns strange. So those kind of a high energetic beam also can damage on that very fragile mask, stencil mask. And again, one of the biggest problem out of this technique is it's kind of hard to make this kind of masks. So we will talk about multiple beam lithography. So this multiple beam lithography does not need any mask. So in a sense, it has the same advantage that electron beam, traditional electron beam lithography can offer. So what people are doing is, as you can see from this cartoon, it has a very large diameter of the electron beam. And then as this kind of a large diameter of the electron beam passing the aperture array, it can just divide one beam to the 13,000 beams. And then there is an arrays. So using this kind of a laser, you can just control each of the multiple beams, and you can just write it down the patterns as you want. So this is the one of the example of the video. So this video will show you how this kind of a multi-beam will work. So from a distance, it looks like looks like a conventional electron beam lithography. So it seems like those kind of wafers just moving around as with the stages movement, and then this kind of one column of the electron beam. But if we just singing inside of this multi-beam electrons, as we just multi-beam electron beam lithography, as we saw from that cartoons, it has one big diameter of the electron beam coming down, and then those kind of big electron beams are separated to the 13,000 finer electron beam. And then as the laser, which is red right now, just touching those kind of objective lens made by the MEMS technology, if then it can just control each of the individual beams separately. So each of the individual 13,000 electron beams can be controlled individually, and then it can just write together like this. So using this way, as you can see from the cartoon, we can just fill that big wafers with much faster writing speed. So this cartoon shows you each of the individual beams writing, and then those kind of writings can fill in those kind of big wafers with a much faster rate. And again, that's the view grab of the column, and then we can just write each of the cell like an stepper can fill the gap. So this is all the details that I talked about. So electron source, and then aperture array, and then here is the objective lenses, which can be controlled by the laser. So this is the example of the pattern transferred to the HSQ as an resist. So this is as we discussed in the previous lecture, this is the negative resist. So for this pattern is an 40 nanometer. The thickness of the resist layer is on 40 nanometer, and then the pattern size is on 45 nanometer images. So it has an isolated dot line patterns, isolated, and then much denser dot and line patterns. And this is an actual picture of the tool. And this tool has 110 beams. So using this kind of an lithography tool, which can produce about 10 wafers per hour. But the price of this tool is much cheaper than that of the stepper used for the commercial production line. So if people can add a couple more tools together, if then just considering this kind of price, you can just meet those kind of throughput, which is on 100 wafers per hour, so which can handle that kind of wafers. So this technology, if we cannot make any more progress out of these conventional optical lithography technologies, using this kind of strategies, we can use electron beam for a commercial production for the next generation of the chip fabrication. So in this lecture, we talked about the way of increasing the throughput of the electron beam. So we talked about electron projection lithography, and then multi-beam lithography. So the electron projection lithography, which is very similar to the optical lithography, but it uses electron scattering based on the density of the masking material. But since it needs to use, it is very hard to making those kind of membrane type or very thin membrane type of the mask structures. So it has some problems to apply this kind of technologies for a commercial production. As to the multi-beam lithography, it does not need any mask set. So in a sense, it is similar to the traditional electron beam lithography, and using this way, we can potentially increase the current throughput offered by the electron beam lithography. So next lecture, we're gonna talk about another kind of technology used by the direct writing, so which is a deep pen lithography, and we're gonna talk about that in the next lecture. Thank you.